All right. Why did I start? Well, couple of announcements. One you've heard ad nauseum, but today'll be the last day for it, because today is the last day to submit your application for the research experience for undergraduates at University of Illinois, University of Arkansas, and Howard University. I've told you about it probably ad nauseum, so if you need any more information, here it is. Today's the day to get the deadline to get it in. Now, I'm guessing that neither of you probably are interested in this, but you may know someone who might be interested in this. It's a line worker training program. It's in partnership with Alabama Power and various utility and contracting companies. What this is, it seems like they got things backwards here. Well, maybe not, I don't know. We are offering training for, and this is on our workforce development area, and basically it's for people who want to learn to be linemen for the county, no, for the power companies, okay? Climbing the poles, running the cabling and stuff like that, driving the big trucks, okay? Program information. Applications are accepted. That one's due today. This one's due on Wednesday, okay? So if you know anyone who's interested in participating in a program like this, they need to get the applications in today, tomorrow, or Wednesday, okay? The training will be starting in June 8th and going to August the 14th. The classes will meet Monday through Friday from 8 to 4, 9 weeks, okay? So there goes summer term. If y'all are interested in it, it's fine if you are interested, okay? The program tuition is $4,150 plus fees, and the fees include books, PPE. I'm not absolutely certain what that is. Hopefully people who are interested in this will know what that is. CDL, that's Commercial Driver's License Physical. Permits and licensing and exam fees. The scholarships are available. They're really needing people, so they've got maybe full or partial scholarships available. The program outcomes. Once you finish this program successfully, you will be OSHA 10, and I'm sure that stands for something. OSHA stands for Occupational Safety and Health Administration, or something like that. So OSHA 10 certification, that's one. Commercial driver's license, you'll get that. That's why the commercial driver's license physical was required up there. Cardiopulmonary resuscitation, CPR training, okay, and basic line worker skills, okay. If you know of anyone who's interested, they should contact us here at Lawson State, the Office of Workforce Development, and Dr. James Gray is the Workforce Development Manager, and his number is one that's, I think, on this campus, okay? His email address is jgray@lawsonstate.edu, or Mr. Tommy Hobbs, who's the Assistant Dean for Workforce Development. I know his office is right over there in the Ethel Hall building. And I believe that Dr. Gray's is probably over there too. I don't know that for a fact, but I think it probably is. And there's more information down here. There's Eventbrite, has a email address or a website. It's called Pre-Apprentice Power Line Worker Application Tickets, and then it has a big long number out there. So the deadline for this is Wednesday. Please get the information out if you know of anyone who's interested in being a line worker for, say, the power company or other folks like that. I've got the information up here. The deadline for applications is Wednesday. And Fred's here. and hopefully a couple others will be coming in soon. I saw Ryan on campus earlier. I thought I saw Josh coming up the stairs, but it may not have been. It was from the back. He hasn't been in? Josh Leatherwood. Okay. All right. Any questions from anything we've covered so far? Oh, one other announcement. I have been assigned to go to Opelika at Southern Union Community College this coming Friday. We'll be leaving something around 6 in the morning and getting back something around 5 in the afternoon. That sort of means I won't be on campus on Friday, okay? I'll be on the road from 8 until 9-ish or so, and then in meetings from 9 till 2, and then driving home afterwards. So I'm not going to be on campus this coming Friday. And because it's going to be 11 hours this Friday, my wife said, good, you can take next Friday off. So I said, yes, ma'am. Okay. So I will probably be not on campus next Friday, too. I don't know what to do. 4 hours of office hours, those are so valuable. I don't know what I'm going to do with 2 weeks without those. I'll probably get way behind on grading and stuff, but I'll try to catch up somehow. Okay. Those are the only announcements I know of. Any questions? Anything coming the other way? All right, well, let's get started from the current slide. This is where we left off last time. We were talking about quadrant surfaces, and we had already talked about ellipsoids, and then hyperboloid of 1 sheet, and then this one of 2 sheets. And my mark on the page was we're ready to start talking about elliptic cones. Now, if you recall, don't go back 1. This hyperboloid of 1 sheet, it truly looks like if that hyperboloid had a smaller and smaller and smaller waist. In other words, this ellipsis at the center just kept getting smaller and smaller and smaller, then at some point that would become almost cone-like. The waist went to 0, okay? It tightened the belt to nothing, okay? And if you look at this hyperboloid of 1 sheet, that was x squared plus y squared minus z squared, now this is over a squared, b squared, and c squared, is equal to 1. If you set that equal to 0, that's exactly how your elliptic cone looks, okay? And again, it's an ellipse. This part is an ellipse when z is 0, or z is any constant. When z is 0, you don't have any points there, because x squared plus over a squared plus y squared over b squared, there's only 1 point that will fit that, and that's equals 0. That would be 0, 0. It's the only way. Anything else is going to be positive. Adding 2 positives together makes a positive. So there's just no way you could get 0 unless x and y are both zeros. So that's one thing. Second thing is, you let either x be 0, then you have, on the yz plane, you have hyperbolas, or x equal any constant, including, okay, wait, let me back off from this. If x is equal to 0, okay, then you have 2 bisecting lines. Y squared is equal to b squared. If move this to the other side, y squared is equal to b squared over c squared times z squared. That's going to be 2 lines that cross like this, and that's exactly what you get. Same thing if you let y equals 0 in the xz plane. You get 2 intersecting, 2 crossing lines like that. But anytime y is some constant other than 0. Goodness, I gotta sneeze. Yeah. Oh, wait. Okay. Then you get your hyperboloids like that. Thank you. Same thing, if x is any constant other than 0, then you get hyperboloids like that. Which basically your conic sections, okay? You get all your conic sections off of here because these are cones. These are, however, elliptic cones rather than circular cones. Okay, so that's probably not quite true. But yeah, that's what it's saying. If you, anything parallel to the xy plane, you get ellipses. Anything parallel to the xz plane or the yz plane, you get hyperbolas. Okay. So those are how you trace it stuff. Any questions about elliptic cones or any of the others we did earlier? All right. Then we have two types of paraboloids. Okay. Well, certainly a paraboloid you would expect will make a parabola in at least one dimension, and this one actually two. And it makes ellipses with the other trace. So, what makes a parabola? You have one variable to the first power and the other to the second. So when x is 0 or some other constant, you have a parabola in the yz plane. Here's the yz plane like this. If you have y is equal to 0, you have a parabola in the xz plane like this. Or if you have z is equal to 0 or any constant, you have ellipses. Well, z is equal to 0, you get 0.00. But z is equal to any other constant, and you have an ellipse. Okay? So your traces parallel to the xy plane are all ellipses, and parallel to the xz plane are all parabolas. Okay? And the yz plane are all parabolas. So that sort of helps with the drawing of these. Now, that's an elliptic paraboloid. And that has first power, one variable to the first power, the other to the second power, other two to the second power, and a plus sign in between, meaning that's going to be, anytime this is a constant, that's going to be a parabola. Ellipse there. Hyperbolic parabola, you have a minus sign in here, meaning they're going to form hyperbolas rather than ellipses. And this is parallel to the xy plane. Okay? Now, and understand this, of course. Sorry. You can move variables around and make the x squared or the y, x squared, z squared, and y over here, and you just turn the parabola like this, you know, or x equal y and z, you turn it like this. So all these you can do that. That's just changing the orientation. Same thing here. Again, you have z to the first power and the others to the second. So that makes it paraboloid, guaranteed. And because when you make this a constant, even the constant 0, not 0, any other constant, you get hyperbolas. Okay. So this is a constant, you get a hyperbola down here. So this is really hard to see. If z is a constant up here, we're not counting 0. 0 gives you a little bit different perspective here. Again, you have crossing lines, and it's kind of hard to see them the way they've done it. But if you have z as a, well, something, z is a constant, it's going to give you parallel to the xy plane, and those are your parabolas, hyperbolas, okay? x or y as a constant, let's do the x as a constant first, or x, start with x equals 0. These are going to be x equals 0, that's a parabola in the yz plane, opening upward. Y is equal to 0, that's going to be a parabola in the xz plane, opening downward. And there it is right there. This is that one, and here is this one. Okay? Now, anything parallel to this below, you've got parabola, hyperbolas down here, or parabolas here, because this continues going up. Hyperbolas like that. They just go in different directions. I'm sorry, I've got these have started the nose are running. All right, so those are your hyperbolic parabola. Another name for this, and we'll see later, is sort of like a saddle. Okay, the horse goes under here, and your legs go across like that. So that makes for a saddle shape, and that's a hyperbolic parabola. A cup with a rounded bottom is not a very good cup. That's your elliptic parabola. All right, and I think that I may have to stop and go down the hall and clear my head. I don't know. Let's see what we can do with this. Here's example 2. I hate to do it, but let me pause this, otherwise I'm not going to be able to. So here's example 2. This is on page 802, chapter 11, Vectors in the Geometry of Space, and these are surfaces in space. It says classify and, you boo his, sketch the surface. So how do we go about classifying this? Anyone want to make an estimate right now of what this could be? Now, here's what I suggest. Think back about what your standard forms look like. Okay, not a parabola, because a parabola always has one term to the first power, the other two to the second. So it can't be a paraboloid. Okay? So let's go back and look at things that are sort of common. Okay? Notice they always leave the x's and the y's and the z's naked. I mean, they may be squared, but they're always written by themselves. Well, not quite by themselves. Things can be under them, but not up there with them. In every case here, that's how the standard forms look. So my suggestion to you is to find the least common denominator of all these coefficients. And what would that be? Say again? 12. Okay, let's divide everything by 12. Okay? Let me get my pen set up. Okay. Now, what that gives us is x squared over 3, right, minus y squared over, or 2 squared, right, plus z squared over 1 squared is equal to minus 1. Okay. Now, other things to watch for, and because I did these over squares, I'm going to do this one over a square too. The square root of 3 squared. Legal in most states? Okay. Now, let's go back again and check and see if we have any of these forms that are equal to -1. I can remember 1s and 0s, but let's see, were there any -1s? That the paraboloids, like Ryan was pointing out to us, needed to have one variable to the first power, the other to the second, so those are out. There's a 0, a +1, a +1, and a +1. All those are +1s, no -1s. How could we make this so that's a +1? Aha! Sounds like a capital idea. So this will be minus x squared over root 3 squared plus y squared over 2 squared minus z squared over 1 squared is equal to 1. All right, now that's looking more similar. Does it ring any bells yet? Okay. Let me give you just a little bit of what I consider things to look for. If these were all plus signs here, that would be an ellipsoid, right? Well, every one of those would be an ellipse. Okay? One minus sign is going to make a hyperboloid of one sheet. Two minus signs will give you of 2 sheets, and I think that's what we've got. Hyperboloid of 2 sheets. Classify, we just did, of 2 sheets. To the wind. No, not that. Okay. All right. So there's hyperboloid of 2 sheets. We have classified it. Now, let's see if that tends to fit. There's your hyperboloid of 2 sheets. 2 minus signs, blah, blah. Looks good. Hyperboloid of 1 sheet would only have 1 minus sign. Okay. Now how in the world do we sketch this thing? There's the fun part, isn't it? So I'm going to try to do my little axes over here. X, Y, and Z. These are not the best way to orient these. More of a isometric or something, but I don't draw those well, so I'm going to stick with this, okay? Now, what do you think is going to be the axis of this hyperboloid of 2 sheets? How about the one with the plus sign? Notice this one, hyperboloid of the 2 sheets. The z squared is the axis. The z is the axis. So that would make what the axis here? The y the axis. Why not? Okay? Now, let's see if we can figure out, with y being the axis, okay, I don't think they label things here. I wish they had. But hopefully this will be, yes.
How is it 1 sheet and not 2 sheets?
Wait, how did I do this? I did not mean to do this. It was Freudian, I guess. Most of the time, I do my axes. Goodness, that was weird. That was going to put it just like the one in the book. I used to do X, Y, Z. I don't know how I did the other. What was your question now?
How is it 2 sheet and not 1 sheet? What's the difference?
Okay. How I look at it, this has 2 minus signs, and a hyperboloid of 1 sheet has 1 minus sign. That's my quick and easy. Okay. Here's maybe a better answer to your question. Okay. And this works pretty well, I think. Okay? Let's try this. Let's say x and y both equal to 0. Is there any way that's going to work? Z squared minus z squared over 1 squared is equal to 1. Will that ever work? At what values of z? Then it would be a negative y. There's no way you can make that work. So x and y cannot be 0 at the same time. So this point is off limits. Okay, and that's true of hyperboloids with two sheets. Unless you've got a translation somewhere there, you're just not going to do. If you let these be 0, then is there any way that's going to be? And the answer is also no. How about these two? Can x and z both be 0?
Yes.
And what would y have to be?
It will have to be 2.
2, you got it. So y equal 2, or this is the minus y-axis, the minus x-axis, and the minus z-axis. Or negative 2 will work too, won't it? Y is equal to negative 2, square negative 2, you got 4. 4 over 4 is 1. So there are your points of intersection of the y-axis, and that's the only axis being cut by this. So now you see this has to be a hyperboloid of two sheets because it never goes to the origin, cannot make it to the origin. It will not ever cut the x-axis or the z-axis. It only cuts the y-axis here. So the next thing I would do was let y be some constant greater than 2. Can't be less than 2. Less than 2, this would then be a small number, and these would overwhelm it. Okay? So there's just no way that's going to happen because, see, if this is less than 2, like 1, that would be 1/4. And 1 minus 1/4 would be 3/4. But this is a negative number, that can't be positive. But if y is big enough, like 3 or 4 or 17 or something like that, then then what I would do was subtract 1 from that and move these to the other side. And then what you have, if y is any constant greater than 2, then what you have here is x squared over something squared and plus z squared over something squared when they're on the other side. Those are ellipses. So basically you're going to have ellipses in this direction. Now let's just go out here to 3. Is that going to be good? Yeah. So this would be 9/4. When y is equal to 3, this would be 9/4. Minus 1 would be 5/4. And then this will be an ellipse of that nature, and it's going to be slightly sort of like this. Okay? And then they just keep getting to be bigger and bigger ellipses here. So basically your ellipsoid hyperboloid of two sheets, it does something like that. Mine are not drawn very well. Okay? But you get the general idea. Ellipses in that direction on your traces parallel to the xz plane, and hyperbole, if you did positions here, you see this would be going like this and like this. So those would be hyperboles in those other two traces. XY plane parallel to the XY plane, parallel to the YZ plane. Those would be hyperbolas. Okay. All right, for me to erase this ugly thing so you can see how it should look. Okay, begin by writing the equation in standard form. Well, they just wrote it in the same form. Write the original equation. And then divide by 12 to get it like we wanted. And notice what they did. They divided by minus 12. Now that took some forethought. They knew that's what they wanted. We just divided by 12, saw that we get the minus 1 on the other side. We needed to change that, so we changed sign. This gives the same thing. And then write the one that's positive first and the other two. So this is hyperboloid of two sheets, because you got two negative signs. Because that forms a hyperbola, that forms a hyperbola. This, when this is a bigger number, move this to this side. This thing's greater than 1, which means y is greater than 2. Then you can subtract this, and you have a positive number here, positive numbers over there. And those get ellipses. Okay? So you can conclude your surface is a hyperboloid of two sheets with the y-axis as its axis. Okay? To sketch the graph, it helps to find the traces on the coordinate planes. The xy trace with z is equal to 0 is going to be, and we didn't do this, we could have, I didn't think about this. That gives you a hyperbola, okay? And the xy plane, when z is equal to 0, xz trace, when y is equal to 0, is no trace, okay, because that can't ever be negative, okay? And the yz place is also a hyperbola. So this is how they drew theirs. Again, find that plus 2 and minus 2. And then in the xy plane, you have a hyperbola this way. In the yz plane, you have a hyperbola that way. Xy plane, nothing. And then anything beyond plus or minus 2, you have ellipses like this. We came up with the same thing. They did their the planar traces, which is a good idea. Okay, but I'm not that used to drawing ellipses either. So anyway, that's how you get a hyperboloid of two sheets. They're skipping example 3, so let's go back and do example 3. Classify and sketch this surface. X minus y squared minus 4z squared is equal to 0. Okay? What was our first trick? Well, this one, don't do that first trick. Ryan was going to point out this is probably a second. Someone's paraboloid, because one of these is just the first power. So then rewrite this. Paraboloids are best looking when they look like this. X is equal to y squared minus 4z squared. Okay? No, plus 4z squared. Sorry. Okay. Now, what kind of paraboloid is this? See, z is equal to that. Now, yes, an elliptic paraboloid. Now, what is difficult about this one is here is your standard form, and you have constants on the bottom, just x squared and y squared at the top. But you have a constant z over here. Well, we have different letters. They're shifted around. But you do not have this. How can you move that to the denominator? Without changing the other. See, this you have a coefficient of 1, this you have a coefficient of 1. That's exactly like you want. But here you have a coefficient of 4. Would that not do it? Let's see, maybe it won't. Wait, let me think. Because, yeah, multiply numerator and denominator by 1/4 squared. No, 1/2 squared, sorry. I knew something was wrong there. 1/2 squared. Because you're multiplying by 1, right? 1/2 squared over 1/2 squared is 1, so you haven't changed anything. But 1/2 squared is 1/4. That wipes that out, and that gives you a 1/4 down here. So there is your c squared. So this would be x is equal to y squared over 1 squared plus z squared over 1/2 squared. Make sense? Second? Not at all. Well, do this, okay? What is 1/2 squared? 1/4. Z squared over 1/4 is the same as z squared times 4 over 1, which is exactly this, isn't it? With a plus. Yeah. So that this is the same as that before I did the other thing. Okay? Now these are not minus signs here. These are just blanks showing what your coefficients, where the coefficient wasn't. Okay. Now, so you've got classify is, what do you say it was? Elliptic paraboloid. Okay, elliptic paraboloid. What is your axis? The x-axis, okay? About the x-axis. Okay, and how you tell this is, okay, when x is equal to 0, okay, again, let me draw my ugly little, here's x, y, and z, okay? Now, notice here, x is always not negative, positive, because these are positive entities added together, okay? Now, it can be 0 when x, y, and z are both 0, then this is 0, okay? But in the rest of the time, this is positive. So don't even bother with the minus x-axis. You can bother with minus y-axis and minus z-axis. Don't even mess with the backside. It can't ever go back there, okay? Now, if you did the xy plane, this is x equal y squared. We know what that is, don't we? X equal y squared? That's a parabola, okay? Now, it's a little different from normal. Normally, we say y is equal to x squared, but this just means x is your axis here. So, it's going to be like this, right? That's supposed to be on the xy plane. Hopefully, it's close enough. And then when we let z be 0, no, that's with z 0, y equals 0, you have x is equal to, I'm going to go back and put it in, 4z squared. Okay? Now that's a parabola as well, but with a vertical stretch, right? So that would be, and this is the XZ plane, this would be this way now. And then if you did the line around those, these are then ellipses. So there is your elliptic paraboloid about the x-axis. And I don't have my dimensioning too well, but you see that's kind of like this. They do more of an isometric form, which shows a little bit better the shapes. But you see these are ellipses this way and paraboloid that way. Okay. You see them? So elliptic, paraboloid. All right. Now, they also do example 4, which they do not show on the slide set. So let me, any questions on this before we delete it? Okay. So let me erase this one, and we'll do example 4 here as well. And if you really want to see a lot cleaner picture, go to larsoncalculus.com for an interactive version of this type of an example. So it says classify and sketch the surface. They said they weren't going to do it, then they turn around and do it. Okay, so here's what they're doing. X squared plus 2y squared. My thing is beeping at me for some reason. Plus z squared. Quit. Okay. Minus 4x plus 4y minus 2z plus 3 is equal to 0. All right. They said they weren't going to do it, then they turned around and did it. What did they do here? You have linear terms with quadratic. Say again? Yeah, it's not at the origin. And here's my suggestion of the technique. They're not doing this on the slideshow. Get your x's together. X squared minus 4x plus blank plus 2y squared plus 4y. I'm not going to put a, but I will, plus blank, plus z squared minus 2z plus blank is equal to, I want to go and move that to the other side, negative 3. Plus some blanks after it. Ah, perfect attendance today. Way to go, team. Okay. Excellent. Okay. Good to see a full class. Okay. Now, with my leaving the blanks there, does this suggest anything you might want to try to do? See the S. Complete the square, at least on 2 of these. How would you do this here in this first term?
Isn't it like you take the middle term, divide it by 2?
Yes. And square it. So negative 4 divided by 2 would be negative 2. Square it would be plus 4. So this would be x squared minus 4x plus 4. Now we just changed the problem though, didn't we? Unless we add a plus 4 over here as well. Well, let's do it down here. Remember I said we had some blanks up there? There, I just filled in one of them. Okay? Now, I should have done this first, but I wanted to get an idea of which way we were heading. What you reckon we ought to do to that before we try completing a square? Ha! Factor out a 2. And that leaves us y squared plus 2y plus blank. And what would go in that blank?
1.
Plus 1. Oops, plus 1, okay. But we've just changed the problem, haven't we? We added not just 1, 2. 2 times 1 there, didn't we? So we need to add another 2 here too. Just so it keeps it balanced, right? See what we're doing? If you add 4 here, you got to add 4 on the other side. If you add 2 times 1 here, you got to add 2 times 1 here, which is 2. And then this one, minus 2z plus 1. So, but that's just the plus 1. Okay, got it. All right, now what do we have? Why did we complete the square anyway?
X minus 2
Squared plus 2 times
y plus
1 squared plus z minus 1 squared is equal to minus 3 plus 3 is 4. Okay? Now I really don't want a 4 over there, do you? What do we want over there? Not as it, yeah.
So when you completed the square on the second one,
This
and
one?
you added a 2 to the other side?
Yeah.
Is it because we factored out the 2?
I factored out the 2 here to give you that, and then left the blank there, and then complete this square. It's easier to complete the square than having a coefficient for that square term. So always factor it out. Be lazy. I mean, it's so hard without doing that, okay? And then this completed the square, became a plus 1, right? Well, you didn't just add 1 here, you added 2 times 1, because these were all into parentheses. So that's why you had to have a 2 there. All right. Now, Patrick wanted a 0 over there. How are we going to make that 4 become a 0? We can't. No, that's not even try. What do we want over there? All but one case, we wanted it, well, 3 cases. But when you had something on the right-hand side, a number on the right-hand side, all but one case, it was a 1. So we want a 1 there. How do we make a 4 a 1? Divide it by 4. So divide this by 4, this by 4, this by 4, and this by 4. Okay, legal? Okay, so this is x minus 2 squared over 4 plus y plus 1 squared over 2 plus z minus 1 squared over 4 is equal to 1. Now, the only thing that's a little messy here, I want these to be squares down here. So I'm going to make that 4 a 2 squared, right? And that is a squared up there. My pen drags sometimes. I want that 4 to become a square. So that's going to be also 2 squared, right? But how do I get the 2 to become a square? So square root of 2 squared. Now I have it. Okay? And what do you think that is?
those are your points.
Say that again.
The -2, 1, and -1 are the points for the center.
Is the center of what?
The shape that we have.
And what shape do we have? That's what I'm getting at. A what? An ellipsoid that's centered, you're absolutely right, at 2 minus 1, 1. So an ellipsoid that's centered at 2 minus 1, 1, and it's going to have major axes on the x and the z translations and a minor axis on the y translation. And if you look at your book, you kind of see that, okay? Kind of looks like an egg, but an egg is flatter on one side than it is on the other. This isn't. But it is at the center of that thing is at 2 minus 1, 1. So you're absolutely right. So don't sweat too much that, but that's what you do if you wind up with a circumstance like that. All right. Now ready for surfaces of revolution. Okay. Any questions? I don't need that. Any questions before we move on? Okay. Then let's move on. Surfaces of revolution. Now this wasn't called for in your, whatever you call it, course description. So let's not spend too much time on it. Let's just do a sort of a slideshow on it, since it's in the book and we're here. The fifth special type of surface, remember the first was a sphere, the second was a plane, was it? Seems like it was. And then the third were cylindrical surfaces, and the fourth was quadrant surfaces, the fifth is surface of revolution. Now look at a procedure for finding its equation. Consider the graph of the radius function, y is equal to r of z, okay, in the yz plane, okay? So, when this graph is revolved around the z-axis, that's y is equal to r of z, so your z-axis is your the axis of revolution, okay. It forms a surface of revolution. When that graph is revolved around the z-axis, it forms the surface of revolution, as shown here, okay. Now here was your original curve, y is equal to r of z, okay, where x is equal to 0, y is equal to r of z. The trace of the surface in the plane z is equal to z0 is a circle whose radius is r of z0. And whatever your z is, if z 7 or 3 or whatever, you know, that's the radius as a function of that. His equation is x squared plus y squared is equal to r of z0 squared. Okay? And then replacing z0 with z produces an equation that is valid for all values of z. Okay. That was a lot of blah, 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 okay? I don't want to spend too much more time on it. So this is what they're saying was originally your z0. Pick some value up here. And then there's the radius as a function of z0. And then when you revolve that around, you get the x squared plus y squared. So that's what you're doing around that r of z0, and then just take out the 0. And that gives you your equation. So these are now all circular things, no ellipses anymore or any other shape, just circular. Okay? Similar manner, you can obtain equations for surfaces of revolution about the other two axes. Results are summarized here. If the graph of a radius of function r is revolved around one of the coordinate axes, then the equation of the resulting surface of revolution has one of the forms here. So if it's revolved around the x-axis, then you don't see axes on this side, just y squared plus z squared. This makes it circles, and then these would be your radii, some function of x. Around the y-axis, you only see x's and z's over here with the squares. These are circular, okay? And then your radius of revolution is a function of y alone. Whatever that squared is, that would be your radius and z-axis. X is y squared here, and r of z squared there. So, find an equation for the surface of revolution formed by revolving the graph of y is equal to 1 over z about the z-axis. Okay? So, if it's about the z-axis, you know the beginning of this equation is going to be x squared plus y squared. Okay? It's equal to, and there's your function of z, 1 over z squared. Okay? There's your radius, is your y, and that's going to be the thing. Okay? How about this one? 9x squared is equal to y cubed about the y-axis. Okay? All right. Just like we saw here, we want this over here to be a function of this alone. Okay? So we want this a function of that alone. But I don't particularly want the 9 to be here. So actually I want this to be x alone. So what is the first thing we've got to do? To make this be x alone. Second? Okay, I would go on and take the square root first. That would be 3x squared, right? Then take the square root, and that would be, didn't want to spend too much time with this, make this 3x squared. You could do what you're saying, and it works out well too. That's equal to y cubed. Then take the square root, and you get 3x is equal to y to the 3/2 power, right? Okay, and then divide by 3. See, I would wait and divide by 3 there. So x is equal to y to the 3/2 over 3. There is your function. So what will be your graph? X squared plus z squared is equal to this thing squared, which would be y cubed over 9. And maybe by dividing by 9 first you would have come up with that. I think you would have, but I was hesitant to do that. Well, let's see if that's what they got. Okay, the first one, the radius function is y is equal to 1 over z, exactly what you saw there. So it'd be x squared plus y squared is equal to r of z squared, which is 1 over z squared. Okay, I'll do the simple, no. Then the next one, to find an equation for the surface formed by revolving that, yeah, they did the same thing we did. That becomes the r of y function, and then you square that. X squared plus z squared is equal to 1/3 y to the 3/2 squared, which would be 1/9 y cubed. Now, here's what I was starting to do, but I was afraid it wouldn't work. For this one, no, for this one. And this is, I don't know if this is where you were heading to. If it was, good for you. But I was afraid it wasn't going to work until I saw, yep, it did work. Okay? So here we have, like you said, divide both sides by 9. Okay? And so you have x squared is equal to y cubed over 9. Okay? And then make it x squared plus z squared is equal to no, you still take a square root. Sorry. Square root, and there you have y to the 3/2 over 3. And then you square that and you get y cubed over 9, which is the same thing we get here. So it really looks like you're just adding the z squared in there. I can't justify that, but that is indeed what's happening. You're just adding the z squared. You get it to x squared, add z squared to it is equal 1/9 y cubed. And it's a megaphone. No, never mind. We don't need that, do we? Okay. And that's the end of the section. All right. Homework exercises here include, I would do all of 5 through 10. Okay. Only the odd number answers are in the back, and only the odd number answers are at calcchat.com, but you should be able to match all 6 of those shapes, surfaces with the 6 equations below. Okay? If you have any problems with them, ask. Bring them to class. Then do either 11 or 13. They're both at CalcChat. 11's at CalcView. Do any of the odds 15 to 25. They're all at CalcChat. 17's at CalcView. You can explore doing 27 or 29. They should be at CalcChat. Then the surfaces of revolution only if you want to try them. You don't need to do those. You're not responsible for them. I'm not going to test you on them. But if you want to follow up what we've just been doing, then you can do those. And again, all the odds 31 to 35 are at CalcChat. 31's at CalcView. Even if you don't want to do them, you can play around with them. Okay. Same thing about 37 or 39. We didn't do those. Those are generating curves for your surfaces of revolution. So basically, this is going in the opposite direction. They give you the generating curve. You figure out what the radius function is. So all the rest of those you can do however you choose of those odds. We're not going to do 11.7. I wish we had time for at least a slideshow, but we don't. So we're moving on to chapter 12. And I passed out last time. No, I didn't literally pass out, but I passed out your... Oh, and by the way, review exercises. Any of these you want to do. Exercise 1's a CalcChat. 3's a CalcChat. 5's a CalcChat. 7's a CalcChat. 9's a CalcChat. 11 is CalcChat. 13's a CalcChat. 15's a CalcChat. 17's CalcChat. 19's a CalcChat. 21, 23, 25, 27, 29, 31, 33, 35, 37, 39, 41 or 43. Finally, we have 2 that are similar. 45 or 47. And any of the odds 49 to 57. You don't need to worry about surfaces of revolution unless you just want to. That would be 59. And don't have to worry about the converting your coordinates. That was in 11.7, which we didn't do. All right. Any questions about chapter 11? I think I was starting to ask, was there anyone who did not get test 1? Did all of you get that? Did you get test 1?
No.
Maybe old, but I'm I think that's everybody, right? Now, again, you're not going to find a problem from every section separately on here, but if you do all these, you'll be doing something that came from every section that we covered, 11.1 through 11.6. Okay? I didn't include 11.7. Okay. Okay. We're starting chapter 12. (12.1). Okay, I don't know what they're talking about. This device can perform faster. USB device is the only USB port that I have. Okay, so give me a break. All right, we'll go from current slide. Okay, yes.
Did you put anything from 10.3 on the test?
Say this again.
Did you put anything from 10.3 on the test? Because I know we started at 10.3. Did you put?
No, I didn't put any, well, no, I didn't put anything directly. I started to fiddle with that. I'd have to make out a whole new test, and I was just too lazy to do so. I figured we covered 10.3. That was sort of left over from last term, so yeah. And I'm trying to remember now exactly what 10.3 covered. Parametric equations in calculus. Guess what? I think, isn't there something on here about a parametric equation? Yeah, number 4 has parametric equation. It's not 10.3, it's beyond 10.3. So even that's incorporated here in a small sense. I see I left off a space after the 0.163 close parentheses. I needed a space there. So you can put 1 if you want to. Okay. That was sort of done. All right, chapter 12. We've been talking about vectors. So chapter 12 is going to pick up and go with this, vector valued functions. Okay. 12.1 is vector value functions, as the whole chapter is named. So we're going to introduce them here, and then in the subsequent sections, we're going to do things with them. Okay? And I think we're probably going to do all 5 sections here. So 12.1, again, introducing what in the world are we talking about with vector value functions. The objectives here are to analyze and sketch the space curve given by a vector value function. Those are always fun, to sketch something in space on a 2-dimensional board. That's really fun. Sketching 3 dimensions on 2 dimensions is fantastic exercise. We'll extend the concepts of limits and continuity for vector value functions. Y'all will eat that up. Okay. So let's first look at what we mean by space curves and vector valued functions. Vector valued functions. A plane curve is a curve that you can draw on a plane. Okay? It's defined as a set of ordered pairs, f of t, g of t. These are parametric equations for the x and the y. Okay? The parameter t, f of t is the parametric equation for the x, and g of t is the parametric equation for the y in the parameter t, together with their defining parametric equation, x equal f of t and y equal g of t, of course, where f and g are continuous functions of t on an interval I. That's the I that contains this t, not x and y, I. This definition can be extended naturally to 3-dimensional space. A space curve, C, is a set of all ordered triples, not pairs, but triples, f of t, g of t, h of t. Again, single parameter t, 3 intermediate variables, x, y, and z. X is defined as f of t, g of y is g of t, and z is h of t, together with those parametric equations, where f, g, and h are all continuous functions of t on some interval I. Okay? Now again, the interval I is the interval for t, not for x, y, and z, or f, g, and h, or anything else. That's the interval for t. A new type of function, this is called the vector value function, is introduced. This type of function maps real numbers onto vectors. Before, a function mapped numbers onto numbers. Okay? Now we're doing numbers onto vectors. The number we're mapping is the t onto the vector r. So here's the definition of a vector value function. Function of the form r of t, notice r is bolded here, indicating it is a vector function of t. It's f of ti plus g of t j. This is in the plane. If you extend it to space, r of t would be f of ti plus g of t j plus h of t k. Now you're into 3 dimensions. That's a vector, both of these are vector value functions, where the component functions, f, g, and h, those are components of the unit vectors I, j, and k, are real valued functions. These have real values. They're not vector value functions. R is a vector value function. These are real valued functions. Whatever t you put in there, you get out an f for the I component, the g, g value for the j component, and the h value for the k component. A real value function of the parameter t. Vector value functions are sometimes denoted as R of t is angle bracket f of t, g of t, just like f, y, or f of t, g of t, h of t, for s, y, and z in space, 3 dimensions. Technically, a curve in the plane or in space consists of a collection of points and their defining equations. Okay? Technically, it has both. Okay? 2 different curves can have the same graph. Okay? For instance, each of these curves graph to be the same. R of t is sine ti plus cosine tj, and R of t is sine of t squared I plus cosine of t squared j. They both have the unit circle as the graph. It's not our normal unit circle, because if you think about it, when t is equal to 0, sine is 0. So you start at 0i, and when t is 0, cosine is 1. So you're starting up here on the y-axis, 1 unit up, okay? And then you're going, as t increases, the sine is increasing and cosine is decreasing, so you're going clockwise. Whereas most of the time we think the unit circle is going counterclockwise, starting over here. But this is still a unit circle, okay? If you square the t before you take the sine of it and the cosine of it, that will still, believe it or not, give you a unit circle, okay? Because you're squaring the parameter, and the cosine of something plus the, say when t is equal to 0, you're up here again, because this is 0 and that is 1, okay? And then as you increase t, the sine is decreasing until you get over here, and then again you're going in a clockwise manner, and you're still on the unit circle. Okay? Now, they have the unit circle as the graph, but they do not represent the same curve, because the circle is traced out in different ways on the graph. The first one will go around 1 time from 0 to 2 pi. Okay? The second one goes around 1 time from 0 to the square root of 2 pi. So it's graphing in a different way, okay? Because as this thing goes from 0 to 2 pi, that would be graphing the same as this, but this thing graphs is 0 to the square root of 2 pi to get the same value. So they would, even though they have the same curve, no, they have the same graph, they don't have the same curve. They're not representing the same curve. Now, be sure that you see the distinction between vector value function R and the real value functions f, g, and h. I mean, we just talked about this. This is a vector, those are scalars. You put in a scalar number, you get out a scalar answer. Put in a scalar number for t here, you get out a vector here. All are functions of real variable t. R of t is a vector, whereas these are real numbers, scalars, for each specific value of t. Real value functions are sometimes called scalar functions, but I just call them sorry, to distinguish them from vector value functions. Okay. Vector value function, a lot of blah, blah, blah here at the beginning, isn't it? Vector value functions serve dual roles in the representation of curves. By letting the parameter t represent time, you can use a vector value function to represent motion along the curve. That's if t is your parameter, and that does represent time. Doesn't have to. You could have t representing anything else. Okay, but if it is, then you're representing motion along the curve. Or in the more general case, you can use a vector value function to trace the graph of a curve. And that's typically what you're doing. This one represents motion along the curve. This one's tracing the graph of a curve. It almost sounds like you're talking about the same thing, except this is actually time, and this is just where your curve is going as t is increasing along some interval. In either case, the terminal point of the position vector r of t coincides with the point either xy in the plane or xyz in space. Okay? So, in a plane, if when t is equal to t0, your x value is somewhat negative, y value is somewhat positive, then you wind up here. When t is equal to t1, x is going positive, y is going a little more positive, so you wind up here. When t is equal to t2, x is even more positive, y is generally a little more positive here, and you see the curve, the trace of the curve here is in that direction. It's not just a curve, it has a curve with a direction because as t is increasing, that's where it's headed. All right. Now, 3 dimensions are always so much fun. R at t0, your x is some positive value here, your y is 0, and your z is 0. You're down here on the x-axis. No, you're not, sorry. Your x is here, y is 0, it looks like, and z is positive here. Okay? Then when you're going to time t1 or next value for your parameter t1, you're going, the x seems to be about the same location. The y now has increased a little, z increased even more. Okay. Now, here's the part that will drive you a little nuts if you let it. Okay, what? No, I'm just kidding. This vector, by everything I can figure, is shorter than that vector. Does it look like it? No, because this is coming toward you. But you see the x values are about the same, so that's not. Y value is definitely greater here, and z value is definitely greater there. So this is a longer vector, but it's coming toward you, so it's foreshortened, I guess is how you say that. So you can't tell by looking at this unless they do put these spots down here, which is the longer vector. But it really doesn't matter. It's just a curve. So the next time you're here, when t is t2, then your x is reduced to 0, your y is increased significantly, your z is actually more like it was. That may be the shortest vector on the group. Or it's not much different from this one, okay? But it's hard to tell that kind of thing when you're plotting a 3-dimensional graph on a 2-dimensional board. So the curve C is again going in that direction, okay? Now, the arrowhead on the curve that we saw there indicates the curve's orientation by pointing it in the direction of increasing values of t. Unless stated otherwise, the domain of a vector value function R is considered to be the intersection of the domains of the component functions f, g, and h. sort of a blah, blah, blah statement, isn't it? Here is what it means. For instance, domain of R of t here, what values can t take on? Well, it's log ti plus the square root of 1 minus tj plus tk. Okay, what values can t take on to fulfill k there? All real numbers. No limit there. How about here? What could t be? The only value.
Positive?
Yes, positive, not even counting 0. So all positive real numbers, this one. So you have to limit this now to all positive real numbers because that's a limitation here. But how about here? What values could t take on? It doesn't hurt to do a little scratch work. I may have just messed up my thing. Oh, goodness. Let me get my pen set up. 1 minus t has to be greater than or equal to, in this case, 0. So that means 1 has to be greater than or equal to t. If you add t to both sides, or turn that around, t is less than or equal to 1. Well, here you said t has to be greater than 0. Here, t could be anything. So now we found out that, let's turn this one around, 0 is less than t. So now we see that 0 has to be less than t, and t has to be less than or equal to 1. So you've got to be between 0 and t, not counting 0, but you could have t there. Okay? So that's now the domain of R. It's less than the domain of F, less than the domain of G, and definitely less than the domain of K. So your R function has a more limited domain because it has to be the intersection of the domains of your other three functions. Does that make sense? All right. So, seems like to me they've just skipped example 1, haven't they? So let's do example 1 first and then go to example 2. Are y'all helping to keep up with time? How are we doing? 10 minutes? Okay. All right. And by the way, in the book they express it like this. The domain of t is from 0 to 1, like that. Y'all are familiar with that notation too, right? Good. Okay. So example 1. Sketch the plane curve represented by the vector value function r of t. I can't write bold, so I'll put a little arrow over it. Is equal to 2 cosine t I, that's a unit vector, minus 3 sine t j, another unit vector, when t is in the interval 0 less than or equal to t less than or equal to 2 pi. Now, there's several ways you can do this. Frankly, if you really are into graphing, probably by the way you first learned it, you'd probably set up a t-table. Not a bad way to do here either, only your t-table has 3 columns now, not 2. Your t is the first column, literally the parameter t, and then your x and your y are the next 2. Okay? You want to do that, or you want to just plug and chug? It's up to you. If it's okay, I'm going to plug and chug. But if you want to see a t-table, I'll be glad to do it. A modified t-table. What you think? Okay. So let's just tick off a few points here. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. Negative 1, 2, 3. Positive 1, 2. Okay. I hope I got enough. I think I do. All right. When t is equal to 0, what is your x value? Really? Cosine of 0 is 1. 2 times 1 is 2, so it's 2i. That would be 2, right? What's your y value? What's your sine of 0? 0. So 2i plus 0j, that would be right here, wouldn't it? This is where t is equal to 0. Okay? How about how about our favorite pi halves? Isn't that a good one? Cosine of pi halves is, so your I is going to be a 0 value. Okay, so you're going somewhere on the y-axis, and what's your y value going to be then?
1.
Sine of pi halves is 1, but minus 3 times that would be minus 3. So there is your t equal pi halves. Okay? How about pi? Sounds like a winner to me. No, okay, no. Cosine of pi is -1, and 2 times -1 would be a -2. So that's going to be right there, I believe, isn't it? Would you agree? Okay. And how about when t is equal to 3 halves pi? What's cosine of 3 halves pi? 0. So the x value is 0, and sine of 3 halves pi is? Okay, so this will be up here at 3. And then I bet you by the time we get back to 2 pi, we're going to be back where we started, right? So would you want to make a guess for what this shape is going to be? Aye, that sounds like an ellipse to me. That looks like it to me, with it going in that direction. Okay? And that is exactly what the book got. Okay. Now, you might ask yourself, how can we verify that? Okay? If you want to ask yourself that, and this says x is equal to 2 cosine t. This says y is equal to minus 3 sine t, right? And we know that this could be solved to be x over 2 is equal to cosine t, right? And minus y over 3 is equal to sine t. Everybody agree with that? What happens if you square both of those? That gives you y squared over 9 plus x squared over 4 is equal to sine squared plus cosine squared. What's that? Oh, yes. So that gives you x squared over 4 plus y squared over 9 is equal to 1, or x squared over 2 squared plus y squared over 3 squared is equal to 1. That means x is a minor axis of 2 from the center, and y is the major axis, plus or minus 3 from the center. Yep. That gives you an ellipse. Okay. That was example 1. Any questions? Make sense? Okay, how much of the time do we eat of that?
We have 3 minutes left.
3 minutes left. Do we have time to do example 2? I'm guessing probably not. So we'll pick up next time with example 2. Okay. And I had 2 marks on that page. All right. And let me give you a few homework exercises in this section. Pretty short section. Do any of the odds 3 through 9. Okay. Do number 11. Oh, and by the way, all of those are at Calc Chat. 3's at Calc View. Do number 11, which is both at Calc Chat and Calc View. Think you could do 13 and or 15. They're both at Calc Chat. You could think about doing example 17, which should be at Calc Chat. And I would say let's stop there, and we'll pick up the rest of those next time. All right, good deal. So you got some in chapter 11, some in chapter 12, and the test to work on, which should be a lot of fun, right? All right, good deal. We'll see one of you tomorrow and the rest of you on Wednesday. Okay, how